Hey guys, in this video I will be going over the proof of the bond angle in a tetrahedral structure, and I'll be determining what that angle is. So if I have a molecule, let's say methane, so methane, right, CH4, what that looks like is if I drew it in a what is it called? Wedge diagram? I forgot what it's called, but it basically looks like this, right? H, H. I have a wedge here, signifying that this bond is coming towards the viewer, and then I have this hydrogen kind of going away. Not exactly away from the viewer, but sort of in the general direction away from the viewer. So these two hydrogens here are in the same plane, and so is this carbon. So if I joined all of these hydrogens with a line, let me just green. Let's do green. So if I zoom in a little, and then if I join these hydrogens, right, the shape that they would form, let's see. My drawing is a little bad, but if I just like drew it here, I have a triangular based pyramid. Okay, so I have a so I have a triangular based pyramid where this here is the base, and assuming that all of the bond angles are the same, I can kind of assume that the carbon will be at the very center of this triangle, or at this triangular based pyramid. And let's just imagine this bond here coming outwards towards you, towards the viewer. That is the hydrogen. This is the other hydrogen going away from you, and then this one, this carbon is here. I'm not sure if you can visualize it, but that's kind of what it looks like. Okay, so if we're gonna calculate the bond angle, or what we're specifically calculating is the angle here, theta. So the angle between each, I guess, dotted blue/black line, that is going to be the angle that we're calculating, and it's kind of safe to assume that between each dotted line there is the same angle. Okay, so just some assumptions. The bond length is the same. So each CH bond you see, that will be a specific length, and there's no different lengths, so all of them are the same. And if all of them are the same, you can kind of see that by, what is it called, side angle side, yeah, by side angle side, if I just drew the center, actually let me label this triangle. OA, B, C, M for the middle. By side angle side, AB is equal to OA, which is equal to, oh, what happened there? OB, which is equal to AC. Basically, all of the green edges are the same length because of the triangles MA, oops, sorry, MAB or MOA or MOC. So, like for example, this triangle here, right? If I just shaded it in, oh, that triangle there from the center of the tetrahedral to A to B, or to the center to A to O, and so on and so forth. So all of them have the same length, and all of them also share the same angle. So therefore AB is equal to BC, so on and so forth. Okay. So, and we're gonna make that length L. Okay. So we have a tetrahedral. Tetrahedral? Nah, I think it's tetrahedron. Yeah, the shape is a tetrahedron, but something that is in the shape of a tetrahedron you can describe as tetrahedral, I think. I'm not too sure about that, but yeah. So each side of this tetrahedron has a side length of L. And if we just look at the base of it, right? Just this base here. Let me label it OAB. If I just label this OAB with the length L. Oh wait, actually, sorry, before I do that, what I'm gonna do is I'm gonna go back to what the goal is, and the goal is to determine what the angle is between this bond here and that bond there. And the reason why I can only focus, or the reason why I can only focus on one pair of bonds is because I'm kind of assuming that it's symmetrical throughout the whole shape, so between each bond has the same angle. That's kind of what I'm assuming for now. It's kind of a bad assumption, but I'm just gonna let that assumption sit there and we'll just go off it. So I'm gonna focus on O to M to C. And how I can represent that is as a vector. So what I basically want to find is the angle between two vectors, OC and, sorry, not OC, my bad, OM and MC. Yeah, there we go. So that's the angle I want to find. And for those who do further math, if you have two vectors, right? If I just drew it here, if I have two vectors, let's say A, and then let's say B, the angle between them, if you want to find that angle between those two vectors and you have those two vectors as a column vector, so A1, A2, let's just extend it to 3 entries, so A1, A2, A3, and then B1, B2, B3. If these were your two vectors and you wanted to find the angle between them in 3D coordinate space, you would use you would use the cross product, and the cross product, right, is this. So A cross product B is equal to the magnitude of A multiply the magnitude of B times cosine of the angle theta, and it's also equal to all of the entries multiplied by each other. So A1 times B1, so A1 times B1 plus A2 times B2, so A2 times B2, and then A3 times B3. Okay, and then from this statement you can rearrange for the cosine of my angle between the vectors, and then you can just sorry, I didn't mean the cross product there, I meant the dot product, my bad. Oh, what happened there? Wrong pen. So let me add this, sorry. So the dot product between two vectors is the magnitude of A times the magnitude of B times the cosine of theta, which is also equal to A1 B1 times B2 A2 B2 plus A3 B3. And I'm just gonna quickly represent this as A dot B. So the cosine of the angle in between them, the cosine of theta, is the dot product between the two vectors over their magnitudes multiplied. Okay, so we'll be using this formula here, and I'll just copy and paste that real quick. So as on monitor, oh, so I'll just keep that in the top corner over there. Oh no, it's not the top yet. So I'll just okay. Sorry, I'm so bad at using this. Okay. So yeah, we'll be using that, and let me actually pull up this diagram again. Just as a reference to the coordinate. Okay. So we're gonna be using vectors to model this. So OM, and we need to find what OM is. But right now we can't describe it with vectors because we don't actually know how far away horizontally and then vertically, and then we don't know the coordinates of this. So let's find the coordinates of this, and let's pretend that it's in a XY Z plane. So here we go. So if I just like drew a cube right next to it, horrible cube. This here is your x-axis, here's your y-axis, and then here's your z-axis. So if we set that OA, oh yeah, sorry, and here's the origin, and if we said OA was the length L, and all of these green edges were the length L, then if I just pick a random point here, this will be L. and then B would be somewhere along in this direction, so I'll label that as B, this as A, and then if I go to the middle of that triangle, so let me actually put it in green just so it matches. If I go to the middle of that triangle and then go up by some length that I don't know just yet, I should have the peak of my tetrahedral. Oh, okay. So here's what it looks like, and the center, which I'll label as green. No, actually, I'll label my center red. Somewhere around here. Not exactly halfway, maybe about 2/3 from the top, or 1/3 from the base. Just an estimate. That's where the, what is this called again? The center will be. Okay. So if OA has the length L, I can say that A has the coordinates along the x-axis of L 0 0. Okay. And then B, well, B is a little tricky because I know that this is a perfect, or the base rather, the base is a perfect equilateral triangle, given that all of the edges are the same length. Right? I know the base triangle OAB is an equilateral triangle, so if I drew that here with a green pen, right, I know that if it was an equilateral triangle, I can just split it down the half, and so my x coordinate of B would definitely be L over 2. Okay, so B has the x coordinate of L over 2. It would have the y coordinate of something that we need to figure out, and then it will definitely have the z coordinate as 0. Okay, so let's figure that out through some geometry. So if I just drew this triangle here, right, just if I split this triangle in half and I get B O, I'll put the letter X here for now. This will definitely be 60 degrees. This will be L over 2, and we just need to find our length or our y coordinate. So we can say that tan 60 is equal to my opposite side, which is y, over L over 2. Okay, and then y would be L over 2 tan 60, L over 2 tan 60, and tan 60 would just be root 3. Okay, so this would be L. This is gonna get messy. Instead of writing it in a column vector, I'll just write it as a normal coordinate, and then hopefully we can just see the transition between coordinates and column vectors. Here, let me rub this all out. So L0 0. Okay, so L0 0, L over 2, L root 3 over 2, and 0. And then we also need to find C. Sorry, here's C. Okay, so C is a little trickier, and how I'm gonna approach this is I'm gonna split this tetrahedron into two pieces. So this is gonna look really weird, but here I'll do it in red. So I'll split it into two pieces. Come on now. So I'll cut it along this edge, and then I'll cut it in half. So along the length, or along the edge AB, I'm gonna cut it in half from there. And what I should have is this shape here. Sorry. There we go. Okay. Wow. Okay, there we go. Okay. And just, I hope you can see that this length O all the way to the midpoint of AB is also the same length as the midpoint of O8 all the way to B, right? Just some rotational symmetry in this tetrahedron. Tetrahedron? Yeah, tetrahedron. Okay. And so I'm gonna use this. Am I? Actually? Am I gonna use that? Yes, I am, actually. Okay, so if I... This is gonna look really weird. Okay. So if I copy and paste this. Okay, and then if I'm gonna magnify it. Right? So let me just expand this image. I think it'd just be better off if I just drew it, so let me actually just do that. Okay. Let's just get rid of this. So if I drew it out here, the shape I would have. Oh my god. There we go, sorry. O C A, and then I don't want to say M because I already put M as the center, so I'll put D. And just know that if I continue this line on, I'd eventually get to B. Okay, so how I'm gonna find a coordinate of C, C1, I don't know, C1, C2, C3, how I'm gonna get there is that, well, notice how in this drawing C is directly above M. So if I just projected the center, so remember I cut the tetrahedron directly through the middle, and here's M. So if I projected M onto the base, I'd get this point here. I'll just call it M dash. And notice how M dash would have the same X and Y coordinate as the point C, but it would have the Z coordinate of 0, or the Z value of 0. So if I can find what M is, M dash is, then I could also find C1 and C2, and given that this length here is L, I could also find the height, because notice how this is a right angle triangle. Since it's a vertical projection, this length here is L, and then if I just have the XY coordinate, right, perhaps I shouldn't do everything in red, but remember that OA is the x direction, so this length here, oh, pen, there we go, this length here is C1, this length here is C2, and so this here would be C1 squared plus C2 squared, all square rooted, right? Just a little bit of Pythagoras. And then of course that this triangle OM dash C is perpendicular to this base triangle. So this is so messy, but sorry, let me just draw the right angle here. No, that doesn't look right. I mean, yeah, it is a right angle, but okay, I'll just draw it there. I don't know if I explained it well, but C will basically have the same x and y coordinate, and then so if I worked with that, I could get this length here, I'll have this length here, and then I can work out the vertical height by doing Pythagoras yet again. C3 squared is equal to L squared plus, I'll put OM instead, OM squared, or C1 squared plus C2 squared. Yeah? Just a little bit of Pythagoras, just because I'm squaring OM squared. I'm squaring OM. Yeah, there we go, sorry. Okay, so we have this here. And so let's find out what C1 and C2 is. Okay, so I split it into two halves. So that also means I split the base in half. And so this angle ODA should be a right angle. And knowing that this here is 60 degrees, actually, I don't think I would need to do that at all. I think I could just, instead of that, let me label it in green. I could just consider this triangle here. Okay? And the reason why I want to consider that triangle there, is because this here would be a length of L. This there, I wouldn't know, but I know that because I split my triangle in, or my tetrahedral in half, this here would be 30 degrees. And so because it's a right angle triangle, I can work out C2 and C1. And if I split this triangle in half again, if I split this triangle in half again, C1, or actually tan 30, would I want to do that there? Wait, doesn't C1 have, oh no, never mind. Oh no, C1 is just 1/2. Yeah, sorry. Because if I just completed this triangle, right, this would end up going straight through M dash. Oh, okay, well, it doesn't look like it, but this would just go straight through M prime or M dash, and it would meet B if I just extended that vertical line. And I don't know if I'm explaining this very well, but C1 is definitely L over 2. If I just check real quick, yeah, so M dash is definitely my length divided by 2, and then using this triangle here, L over 2, 30 degrees. I'm just using OM dash and the midpoint of OA. Sorry. I'm gonna have to probably add another letter here. E. This would be L over 2. So my x coordinate, sorry, no, not my x, my y coordinate here would relate to tan. So tan of 30 times L over 2 again. And then tan of 30 is just root 3 over 3. So this would be L root 3 over 6. Right. Am I bugging? 1 over root 3. Yeah, it is. That is, yeah, it is. Okay. And then using this, right, L root 3 over 6, 0. I just, and just remember that this is C1, this is C2. And then I can find C3. C3 is equal to the square root of L squared plus L squared over 4, just squaring C1, plus L squared times 3 divided by 36, and then what this would equal to, let me just separate this actually, be the square root of L squared 1 plus 1 over 4, 1 over 4 plus 1 over 12. Okay, and then this would simplify to 12 plus, sorry, plus times by 3, so 3 over 12 plus 1 over 12, sorry, over 12, and it's with an L outside, L square root of 12 plus 3, 15, 16, 16 over 12, 4 over 3, so this would be 2L over root 3. Okay. So, which is equal to, I said L over 2. What did I say? Here. L over 2. L, I could just leave this as 2 over root 3, since if I rationalize this, this will become, well, it will be equivalent to that. So I'll just leave it like this, and then 2L over root 3. Okay. Now, let me write it here. Actually, let me write it in blue, just so it's a little nicer on the eyes. L 0, 0. B is equal to L over 2. L root 3 over 2. 0. C is equal to, what was it? Here. L over 2. L over 2 root 3. 2L over root 3. Did I have any other coordinates? No. No, I don't think I did. Oh, okay. Fine. Okay. So, here. Okay. So I think these points, these 3 points here, are enough to define the vectors of this, or it's enough to determine the shape of this tetrahedral. structure. Oh, okay, that got rid of it, so let me copy and paste it. Do I hide which one? Uh-oh. I think I'm gonna have to copy and paste again. Okay. Okay. So again, OA can be defined as this. OB can be defined as this as a column vector, and the same thing with C. And I'm just gonna go through a little bit of, I guess, reasoning. So because I want to find the angle between OM and MC, the angle between OM and MC is also the same as the angle between AM and MC. So if I just said the angle of these two, if I wrote it like this, right, the angle between OM and MC is also equal to the angle between AM and MC, then I could just work out AM to MC. And let me just think. Oh yeah, which is also equal to the angle between PM and MC. And the reason why I want to work with these two vectors is because conveniently, I'm not sure how I can represent this, but if I zoom back in onto my tetrahedral, and then I use a different color, so like let's say red, right? So here is my center, right? Why is it not? Okay, so here's my center and here is B. If I drew, if I connected M and B, and then I carried on that line would eventually hit OAC. And I I really hate how this is like an instinct for me, but actually, no, no. But before I even start from B and C, I'll actually start from C to the middle of the tetrahedron. So if I start from C and then I made a line to the middle, and then I carried on that line, it would eventually hit the base triangle, the base of this tetrahedron, at a 90-degree, right? If we just like kind of think about it like a pyramid, right? If we just hung a string, it would go through the middle and it would touch the base at a 90-degree angle. And because of the rotational symmetry of this shape, I can also say that if I connected a line from B to the middle and then I extended that line, it would eventually hit this triangle OAC in the middle at a 90-degree. And what does that mean? Well, that means the vector MB, or BM, MB, whichever one, I'll stick with BM. Uh, this suggests, or this implies, that BM is perpendicular to the plane OCA. So this plane, or this triangle OCA, how can I highlight it? Okay, opacity, turn that down. Let me turn that the size too. Oh, it's a little too small. So this plane here, right, the vector MB to the center all the way to the vertex B, that vector is perpendicular to the plane OCA, which also means that BM is a normal vector. So BM is a normal vector to the plane OCA. And I'm just gonna play. I'm gonna plane. What? I'm gonna call this plane capital Pi. Okay. So, in short, BM is perpendicular to the plane Pi. Okay. And because we have these two direction vectors OA and OC, I can describe the plane OAC with these two vectors. So pi can be described as the position vector being it goes through the origin, so I could just say the 0 vector plus some scalar of OA plus another scalar of OC. And what that looks like is, well, the 0 vector, all of its entries are 0, so this won't really matter. This would look like lambda L00 plus mu of okay, so L is a constant, so we can just bring that out, and instead I should really write 1, since L is a constant anyways, and if I bring it out, I can absorb that constant into lambda. The same with B, so remember that B is here, but I can also say 1/2 root 3 over 2 and then 0. That looks really messy. Actually, I could also absorb that additional 1/2, so I could just say 1 root 3 and 0. So that is my plane. This is the equation of the plane. And then if I wanted to find a normal vector of this plane, right, I would have to do the cross product. Jeez. Oh my god. Cross product between these two basis vectors. So 1 0 0 cross product 1 root 3 0. And what that is the same as taking the determinant of the matrix I hat, j hat, and k hat with all of the entries as such. So this is just OA and then OC just transposed. And what that is equal to I times 0 minus 0 times root 3, so 0, minus j hat times 1, okay, so just 0, and then plus, is that right? That doesn't feel right to me. Oh, sorry. I wrote the wrong coordinate. I wrote B down, sorry. This is supposed to be, what is it? Oh, so the whole thing has changed. Sorry, this is supposed to be OC, and I wrote down the vector OB. So let me just rewrite this. L over 2. So I'm going to absorb all of these L's. So 1/2. 1 over 2 root 3. And then 2 over root 3. And so because of that, I have to change all of this now. So this becomes 1/2 1 over 2 root 3 and 2 over root 3. Okay, so this also changes. 1/2 1 over 2 root 3 and then 2 root 3. Okay, so what that does now is it changes all of this. So I had let's see, okay, it's still gonna be 0. Sorry, just gotta scratch my arm. Minus j hat times 1 times 2 over root 3 minus 0, so 2 over root 3 plus not j hat, sorry, k hat multiplied by 1 over 2 root 3 minus 0, so 1 over 2 root 3. Okay, and what that looks like as a column vector would just be 0 2 over root 3. Actually, because a normal vector can still I don't know how to say this, but I could just say the normal vector as, okay, actually let me actually write it down. 2 over root 3 and 1 over 2 root 3, and then let me just multiply everything by root 3, and what I will get is 0 2 and then 1 over 2. So this, oh yeah, sorry, negative 4. So this would be my column, not my column, my normal vector, right? So my normal vector would be in the direction of negative 2. So somewhere like this, because remember that this is the x direction. And if I just continue drawing that, this is the y direction, and then that's the z direction. Negative 2, or well, okay, let me start with 0. So it would have 0 horizontal component. It would have a component of magnitude 2 but backwards, and then it would have vertical component of 1/2. So this is what my normal vector would look like, right? If I just drew it again, maybe in a different color. Let's not go with that. Let's go with a different color. Purple? Pink? I don't know. So my normal vector would look like that, and I'll just label that n1. Okay, and then remember that the normal vector of n1 is still pointing in the same direction as b to m, or m to b, whichever one. It's just a negative, well, the direction is still the same. So n1 is facing, or is parallel to bm, and that's all we need. So we just need a vector that is parallel to bm, and so we have this here. So let me just write that down. n1 is equal to okay, I'll negative I plus 1/2. Sorry, no, that's a lie. It's negative 2j plus 1/2 of k. And then my other normal vector of my plane OAB, and remember the logic being, or the argument being, that the normal vector here, all I need, the normal vector of the plane OAB just needs to have the same general direction of M to C, and we can see that M to C is just being vertical, no horizontal. Yeah, it is vertical, but I don't know how to say. I don't know how to describe the direction towards the Y direction. Usually it would be vertical, but I guess it doesn't have any depth to it. It doesn't have any horizontal component to it. It only has a Z component, if that makes sense. So I could just say that N2 is equal to k hat. Yeah? And what k hat is just a unit vector in the Z direction, or along the Z axis. So it's just 0, 0, 1. Yeah? Okay. Now, time to work out the angle between these two vectors. So remember that, let me actually just kind of fortify my logic a little bit more. So if I drew this section here, right? Can you write? There we go. If I drew this section here, right? So C M B. Actually, let me draw the methane. So CH H, right? And of course I'll draw the rest. So I'm specifically looking at this section here, and as a if I model it as a tetrahedron, right, using the same coordinates, it would be C M B, yeah. And I just wanted to find this angle here, and then because I said that these two normal vectors would have the same direction, well, I could face it like this if you wanted, or I could face it like this by just timesing the vector by -1. So maybe I should just write 2 g hat plus 1/2 k, because it's still a normal vector nonetheless, it's just pointing in the opposite direction, right? So just comparing it. So this is n2 and this is n1, and this here is still my angle theta. And going back to the start of the video where I said the cosine of that angle is equal to the dot product between those two vectors divided by the product of the magnitudes of those vectors. That's quite a mouthful, but I hope that makes sense. So just kind of highlighting this kind of logic here. If I just printed this out, tell me that, okay, yeah. So I'm just gonna move that over here, and then again, what was it? -2 j plus 1/2 k hat is equal to n1, and 2 was equal to, it was just k hat, because as I said, it's just a vertical vector. So the dot product between these, oh yeah, and let me just write them as a column vector. So this would be 0, 0, 1. This would be 0, -2, 1/2. Yep. So the dot product between these two, again, I said it would be 0 times 0 because that's a1 times b1 plus negative 2 times 0 plus plus 1 half 1 half times 1. So overall 1 half, and again this is equal to magnitude of A, magnitude of B, cos of my angle. And then let's find out the magnitudes of my vectors. So 1 half is equal to, let's see, so the magnitude of my normal vector 2 would just be 1, and then the magnitude of my second, or n1, would be the square root of 4 plus 1 over 4, so square root of 4 plus 1 over 4 times cos of theta, and then the square root of 4 plus 1 over 4 would just be square root of 17 over 4. You can simplify that as root 17 over 2 cos theta. And then I can just cross these out here. Say 1 over root 17 is equal to cos theta. And then theta is equal to inverse cos of 1 over root 17. And then what that equals to is, let's see, sorry, root 17. $75. So, oh, well, actually, 75.9637 degrees. But that is the acute angle. Oh yeah, sorry. Let me just say that. Okay, so there is an acute angle between these vectors and also an obtuse angle. So this here is what I just calculated for it to be 75. I'll just say 76 degrees. And so because the bond angle again was obtuse to start with, I'm gonna have to subtract that from 180. So 180. Jeez. Oh my god. Okay, fine. I'll just leave my 8 like that. 75.9637. Let's see what that is. 180 minus that. 104.036. Wait, that doesn't seem right. Isn't it 109.5? What?
Excuse me, Longvu, but I think you made a mistake in one of the previous steps. Because the bond angle is tetrahedral structure is 109.5.
Yeah, Maz, you are correct. The bond angle should be 109.5. So I should have made a mistake somewhere. Let's look for that mistake. Okay. Apparently I don't know my Pythagoras. Okay. So apparently I don't know my Pythagoras' theorem. Sorry. Control Y. No, that didn't do anything. Oh, what was that? Why did I make everything so ugly? Alright, anyways. Apparently I don't even know my Pythagoras' theorem. This is wrong. This is supposed to be a minus. Sorry about that. Where is it, bruh? Which layer is it? Ah, here. No? Why is it not? Okay, there we go. Sorry. My mind just blanked. This is supposed to be a minus because this here is the hypotenuse. This here is just a component side or a small side, and then this here is what I want to find. M dash, I think that was supposed to be C. Oh yeah, it is C there. So M dash C is your smaller side, and so it should be L squared minus the square of the square root. So square root cancel out, and what you get is this. And then, of course, this is supposed to be a minus as well. Let me do it in a different color, kind of like green penning or some. I was gonna say, okay, I'm not gonna say it. That's a bad word. I'll do it in a. No, I shouldn't. I'll do it in a red pen. I'll continue doing it in a red pen. So that's supposed to be a minus. Minus all of it actually. Yep. So this here is supposed to be. Let me rub this out as well. So that come on now. Minus, 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 minus. Okay, so let's do this again. 12 minus 3, that's 9. Minus 1, that's 8. So 8 over 12 simplifies to 2 over 3. So this should be root 2 over 3 times L. Root 2 over 3 times L. There we go. And then again. Oh, okay, bro. Pro. Okay. Root. Why is it green now? Root 2 over 3 times L. This is so tedious. I hate it. Okay, so again, what did I just change? Sorry, what? Oh my god. The 3. Alright, okay. So, in turn, this makes it such that this is supposed to be root 2 over 3. And then this is also supposed to be root 2 over 3. And then doing the determinant again. Or the cross product rather. So let's just do this real quick in our head. 0 times 0, so not 0 times 0. 0 minus 0. Actually, I'll just do this. I'll add a negative there. 0 times 0, so that's just 0. G hat. This is supposed to be changed. Root 2 over 3. So this becomes negative root 2 over 3. And then k hat, let's see. 1 over 2 root 3. Okay. And then again, if we just factor out the 1 over cube, not cube, the 1 over root 3, this becomes, oh well, the normal just shrinks down by a factor. Or actually, no, it gets multiplied by a factor of root 3. And then this becomes that. So there you go, that's my normal vector now. Wait, doesn't that change everything now? Oh, it's just root 2, okay, fine. What was root 2? Sorry. Okay, yeah. So this, can I write is over root 2 root 2. 1/2 is still there. The magnitude is no longer this, so I have to rub this out. Everyone makes mistakes, guys. It's okay. So this becomes 2 plus 1 over 4. That's just 9 over 4. Unless my math is terrible. Yeah, that is 9 over 4. So this becomes 3 over 2. Where is it? 3 over 2. 3 over 2. Cancel out the 2's. Divide both sides. You'll get 1/2. Sorry, not 1/2. 1/3 is equal to cosine of 30. And then theta, my angle between my bonds, is inverse cos of 1/3, which isn't 50, 75. It isn't 75 anymore. It's 70.528. 70.528. And then so 180 minus all of this, minus answer 109.47 degrees. And there you go. In chemistry, you are taught that the bond angle in a tetrahedral structure is around 109.5, and yes, this is around 109.5. There we go. Thank you very much for watching. Yeah, sorry for that mistake. Thanks for watching. I hope you enjoyed.